Okay, it's just connecting now. Good morning, good afternoon, good evening, everybody. Thank you for joining. I'm just going to give it about 30 seconds for people to be able to connect, and then we'll make a start. I think the last session just went over by a few minutes, so I'll just give people a chance to move over from there to here, but we are currently live. Okay. Great. Okay. Let's make a start. So thank you so much for joining, everybody. This is the last of our innovation presentations of this remote sensing day. We've got a really good presentation here from Palindrome Remote Sensing. So Mark is going to be, who is also the founder and the managing director, is going to be speaking on ensuring and improving weather radar data quality. It's about 15 minutes. So I'm going to hand straight over to Mark so he can introduce himself further. And any questions you have, you can put them into the Q&A section. Alternatively, you can reach out to Mark directly from the platform straight after the session or in the coming days. So Mark, over to you. The floor is yours, and I'll be here if you need me.
Thank you very much. Good evening, everybody. It's evening here in Switzerland, so it's a pleasure for me to give you our view on how we think radar operators could ensure and improve the quality of their weather radar data. I'm from Palindrome Remote Sensing. I'm the founder and managing director of Palindrome Remote Sensing. Our company is not as large as Vaisala or Dematronic or Leonardo. We were founded 4 years ago from former weather radar scientists that were working at Meteor Swiss, and we were dealing with calibration issues of weather radars. And so from there, the idea came to found this company, because we realized that we're not the only ones struggling with calibration issues and data quality issues. So we're located in Switzerland. We provide radar services, and I'm going to talk about our main product, which is the Polarimetric Radar Target Simulator, which is an instrument that helps to ensure radar data quality and to calibrate your radar. And so this company was founded with the goal to enable radar operators to get full benefit from their usually costly infrastructure. So I think everybody in the audience is aware of the importance of accurate weather radar observations. So weather radars are used to issue warnings from floods, from landslides, debris flows, hurricanes. But they're also used for flood mitigation, like in the city of Tokyo. The radar data is used to control sewer systems, but there's also research done, a lot of research done in terms of precipitation microphysics and dynamic meteorology. So I've put this figure here from Nova Friburgo, which is in the a mountainous region close to Rio de Janeiro, where disastrous floods 10 years ago caused these landslides. And the reaction of the Brazil government on these floods was the foundation of CEMADEN, which is the government agency to mitigate those risks by building quite a large weather radar network. But weather radars, they used to provide pictures, like pictures for the TV, like people watching TV and the weather forecast, they can watch how the rain front's passing in. But if we don't want to have pictures, we want to have data, because with data we can do physics, we can do forecasts, we can do data fusion, we can do assimilation, comparisons, and all those fancy things that people nowadays do. But to go from pictures to data, we need to have our instrument calibrated. And so the foundation of all this is a well-calibrated instrument. Now the problem is written here with a statement of the World Meteorological Organization. It's not, it's from 2012, but it's still the case. So the World Meteorological Organization, they say that somewhere in the world, there are a lot of radars, and not all of these radars are well calibrated. So some of the calibration the calibration techniques are insufficient, and calibrations are inadequate. So this is what WMO says, and the reason is that there is quite a high complexity in the calibration of modern radars, because these radars, they consist of antennas. So you have to calibrate the antenna, you have to calibrate the pointing. Radars consist of transmitters, so you have to calibrate the transmit power. The radars have receivers, so you need to calibrate the noise figure. And the radars have radomes, so you need to calibrate the loss of the radome, and the loss of the radome changes when the radome ages or when the radome is wet. And modern radars are polarimetric, so this increases the calibration complexity, I would say by a factor of 3 or 5, because you get much more information from a polarimetric radar, but the complexity is also much higher. So there are some requirements for a good technique for weather radar calibration. So we think that such calibration should be traceable. So it should be a metrological calibration chain. It should be easy to use because there are already a lot of complicated techniques. It should be end-to-end, and end-to-end means that we want to calibrate not just one aspect, but the whole chain. So we want to calibrate the transmitter, the antenna, the radome, and the receiver, so the whole system. Because most of the radars are polarimetric nowadays, we need to have a polarimetric calibration system, and we need a high accuracy. And these are some figures here, like which are the, I would say, minimum accuracy requirements we have. And it should be for SC and X band, which are the bands that are used at meteorological agencies. So what is our proposal, or what is our solution? So we have developed this instrument, which is called Radar Target Simulator. This is an instrument shown in this sketch here. So there is a radar. The radar sends red pulses, and our instrument sends back the green pulses, and these pulses are modulated in a way such that on the radar screen a virtual target appears. And this virtual target is a very accurate calibration target. So you see it on the radar screen, and you can compare your radar data against the predefined conditions of this target. So, and this is a setup you see here. So there is a radar in the red, where the red dot is, and this is our instrument in a distance of about 2 kilometers. So for the radar experts in the room, I have put those figures. This is actually what the radar sees as a virtual target. So we have generated a target at 30 kilometers with a reflectivity of 55 dBm. And you see here on the radar screen, a target appears at almost 30 kilometers and with a reflectivity of slightly more than 55 dBz. So this is actually a very well calibrated radar. And the targets we generate, they are polarimetric targets. So there is also an image for the differential reflectivity here. And for those who are not experts in radar, so that the take-home message here is that we generate a target, and you compare the value you have here, so those 55 dB, to value you have set on your instrument, and the difference is actually the calibration offset. Now, another slide for the experts. This is for polarimetric radar data. So this is a virtual target of polarimetric radar data. And this is just to show that our instrument is capable of generating full polarimetric targets, cross-polar coloration. So the target we have generated has a velocity of -4 meters per second. So this is shown here, spectral width, differential phase. So it's all there. And so the last technical questions, these are time series. So we take the value of our generated target and plot a time series of what the radar sees. And now here you see this is the target has a value of 55 dBz, and the target generator and the radar sees 55.5 dBz, so there is a difference of 0.5 calibration difference. This is the velocity, so our target was generated with a velocity of -4 meters per second, and what the radar sees is almost -4 meters per second. So there is a very slight offset of, I would say, negligible offset. We can also calibrate the antenna pointing, which is an important factor. So if pointing is not well done, then your whole radar data set is not well geolocated. This is the half power beam width of the antenna. That is a very important parameter in terms of translating received power into radar reflectivity. So what are the advantages and limitations of this target simulator approach? So I think the main advantage is that what we do includes the full transmit and the receive path of the radar. It's not just one aspect. We calibrate the whole system, and so there are there is a wealth of transmit path measurement possibilities. So we can really analyze like the aging of your transmitter or pulse width, and so there are a lot of information on like how is your system degrading, or how is the health of your system. So we can also simulate a lot of different reflectivities, different Doppler speeds, so we can basically test the whole dynamic range and linearity of the system. There is one limitation, so because our system is set up at one point, we only calibrate the radar at one point. And if you want to have calibration at different locations, you need to move around our instrument. So highest possible accuracy, that's the main goal. And how is this achieved? This is achieved by collaborating with the Swiss Federal Office of Metrology, which is kind of the National Institute of Standards. And this office makes sure that actually the target we generate is traceable to SI unit, and it has really the accuracy that we claim it has. So there is a lot of testing done in the laboratories of Metas just to make sure that what we claim is really our instrument is capable of providing this. So just some impressions from our customers all over the world. So we were lucky to have some measurements during the Olympic Winter Games in Korea, together with Korea Meteorological Administration, Kyunpook National University. We were doing a lot of measurements with EPFL, which is a technical university in Switzerland, with the Swiss Army that uses a lot of radars and uses our instrument to calibrate these radars. So we had some measurements with MetaPress in Austria and with Chengdu University of Information Technology in China. So we want to expand, of course, these customer range. And what we can offer is shown here. So what we can do is we can we provide and we offer a high accuracy weather radar calibration service. We also provide independent radar assessment, so it's not always easy to actually assess your own radar, because that's complicated, and this is what we realized when we were working at Meteor Swiss. So we're independent from the radar manufacturer, and we can make sure that the radar is conformant to the specifications. And we can also set up whole calibration networks. So if you want to have a continuous calibration and not just a calibration once a year or twice a year, we can set up networks like this such that you have a continuous calibration throughout the year and a continuous analysis of your system that provides also predictive maintenance. And the whole goal, or the only goal of this, is that we really want that you get the most out of your weather radar data, because weather radars are costly infrastructures, and you should benefit from this infrastructure the most. So I'm happy to answer any questions, and otherwise I'm happy to chat with you or to get in contact with you. Thanks a lot.
Thank you, Mark. Really appreciate that. Very, very, very informative. Yes, I hope everybody enjoyed that. We do have a bit of time if anyone's got any questions. If not at the moment, then please do make your way today over to the remote sensing part of the, excuse me, sorry, I had something over my camera. If you can make your way over to the remote sensing tab, then you will be able to see Palindrome on there, and you'll be able to get directly in touch with Mark and speak one-on-one. I'd be more than happy to answer any questions that you have. Marky, thank you so much. We have one more session just coming up for the day. But Mark, thanks again. Really appreciate your time. And again, please do reach out directly to Mark. You can find him on the system and find them in the remote sensing tab. Yeah, thanks again. We'll see you in the next session. Mark, thank you, and see you soon.